moving things through carriers across cell membranes. We have talked about simple diffusion across cell membranes, not using a channel or a carrier or anything. We've talked about diffusing things through channels when necessary. And we've talked about osmosis, which is just a special instance of diffusion. Now what I want to talk about is diffusing or moving things across a cell membrane through carriers. And with this one, we're going to be talking about diffusion, but you can also use carriers for different types of transport, like active transport. So what is going to happen in this instance, like you're seeing in this picture, is something will bind to a shape-specific binding site in a protein, and then the protein will change conformation to move it across the cell membrane. And that was what we saw. It doesn't show it quite as well here because it doesn't show the shape-specific binding site, but still, here it is. It's changing shape and conformation to get the thing across. So what makes a carrier different than a channel, remember, is that carriers have shape-specific binding sites for the thing that they are going to carry. The other thing is, if you have a shape-specific binding site, it's really, really common and easy to make them subject to regulation by other molecules. For instance, something bound right here, not here where it was going to get carried, but right here, and it changed the shape of the binding site, then you could make this carrier work poorly or better. So really common for carriers to have shape-specific binding sites and be subject to regulation by neurotransmitters or hormones or paracrine agents or whatever. So the other thing about moving things through carriers is that the amount of carriers that you have impacts the transport rate really dramatically. So if you just looked at simple diffusion, not through a carrier, then there would be a pretty direct correlation between the concentration gradient and the net flux. So a higher concentration gradient would make it move faster, a lower concentration gradient would make it move more slowly. But what about diffusion through a carrier? What happens with diffusion through a carrier is that there's a direct correlation for a while. As the concentration gradient goes up, the net flux goes up. But then what happens here? What happens here is called saturation, and you've used it in reference to enzymes before. But here it kind of means the same thing. It just doesn't have to do with enzyme activity. It has to do with transport rate or net flux. What's really going on right there is, if I had 20 carriers for the thing that I was trying to carry and they were all full, it would really limit the rate of transport, the net flux, and you can't go any higher because you don't have any more carriers, even if you got a greater concentration gradient. So anything that's carrier mediated is subject to saturation limits. So the rate of transport can't increase once all the carriers are full. It's not going to trash the transport rate. It's just going to hit a limit. Okay, so now let's talk about facilitated diffusion. So remember, our rule was if we could move something by the cheapest or fastest way, we would do it that way. So hopefully you guys remember that simple diffusion straight across the cell membrane is really fast. And then diffusion through a channel was slightly slower because it limited the locations that you could move. And then doing it this way, diffusion through a carrier is going to be slower still. So why would you do it? Well, remember that you will do it when you have to, when all of the other ways don't work. If I'm trying to move glucose is water soluble. It's not going to diffuse straight through the cell membrane. It's too big for a channel. And so plan C is going to be diffusion through a carrier, which is going to be slower. It's still free as long as the concentration out here is higher than the concentration in here, and you want it to go in. It's still only going to move things down their concentration gradients if we're talking about this, which is facilitated diffusion. This is a really common way to move mid-sized water-soluble molecules like sugars and amino acids. And they're going to move down their concentration gradient through specific protein doors, right? Carrier proteins. And think of it like a revolving door in which the door has to do some of the moving. It doesn't require ATP. Even though the thing wiggles, it really only wiggles because the binding makes it change conformation, and then the dropping off makes it change conformation again. So the binding makes it change once, pew, the dropping makes it change another time. So it moves something through a specific carrier protein down its concentration gradient. And the net flux is still, high to low. And this is a really, really common way of getting amino acids from the blood, plasma into the cells. It's a really common way of getting glucose inside cells. It's really used all over the body. And just to give you a visual, even though this one shows far more, let me just show you this specific facilitated diffusion.
If the molecule is not recognized, the channel will not open to allow the molecule.
Let me go back to here. Thought I had it just at the right place.
These permeases only allow specific types of molecules to pass through their
Binding,
channel.
putting it in.
The channel contains a recognition element. If the molecule is not recognized, the channel will not open to allow the molecule to pass into the cell. Osmosis is a special kind.
So we already did osmosis. Okay. So I'll link this one for you. All right. So that is facilitated diffusion and just generally mediated transport systems. All mediated transport systems use a carrier as the mediator. Although textbooks disagree on that. Sometimes they include channels, but for my purposes and your textbook purposes, let's say that mediated transport systems use carrier proteins. And in the next video, which is going to be like a little challenging potentially, we're going to talk about using a carrier protein to move something the opposite direction that it wants to diffuse. And this is going to be active transport. Okay.